Well, good morning. This is 11:01 on Tuesday, the 17th of October, 2017. Math 237. Sorry about my voice. I went to the game Saturday and yelled too much, so sorry about that. But anyway, we are supposed to be linear algebra. Right now, I'm the only one in the room, so hopefully the others will be coming soon. Where we left off, let me give a few announcements. First, office hours. This is beginning of the second mini-term this week. And the first mini-term, I had a physical science class Tuesday, Thursday afternoon, started at 1:15 and went until 5:45. It was a mini-term, class and lab, so that's why it took so long. So that meant my only office hours were at the end of this class, 12:15, till that one started at 1:15. That was all I had. And in fact, I had eaten my lunch during those office hours. And that was the only time I was in the office between 8 in the morning and 5:45 for more than just a few minutes at a time. So, second mini-term, however, Physical Science 2, that class is needed by the automotive students. In fact, they are the reason that's offered on mini-term, because the Ford, Toyota, and GM programs, the second-year students are at the dealerships for the first mini-term and on campus for the second mini-term. And those that are taking the course this term have a class that goes, an automotive class that goes until 3 o'clock on Tuesday, Thursday. That means I can't start the physical science class until 3:15. So therefore, for the second mini-term, I have 2 hours of office hours I didn't have at the first mini-term. Have my lunch was 12:15 to 1:15, and then office hours from 1:15 to 3:15. Though I'll eat anytime in there and deal with students anytime in there. But officially, those are it. For instance, today, the student said he was coming at 12:15, so I'll deal with him then I'll go eat lunch, and then I'll come back. So I usually eat in my office. I just got to go down and buy it today because I was on campus late last night and didn't have a chance to make my lunch last evening when I got home. Okay, that's the first change of office hours. Number two, normally, and this continues the same, my office hours on Monday, Wednesday are 3:15 to 5:15. However, tomorrow, Wednesday, I've got a meeting on the Birmingham campus, so I'm going to have to leave here shortly after my 3:15 class is over with, head to the Birmingham campus, and my meeting there is from 4 to 5, and then I'll be on campus for the rest of the afternoon until 5:15. So what few office hours I have will be on the Birmingham campus. It'll only be maybe 15 minutes before the meeting and 15 minutes after the meeting, and that's all office hours I have, but they won't be in my office here, they'll be there. All right, this is also the week that they're supposed to open the midterm progress reports. What that means, I need to have grades. I know both of you have turned in your first test, it would be nice to have your papers too, at least one of you, sort of pull up the score that you had on your test, so that I don't have to do a midterm progress report on you. Not that it bothers anything, it's an easy thing to do, but it's no negative implication on it, but just you need to, it would be beneficial to have that done. Okay. And so get me something by Friday if possible. Okay, what else? I think that's about it. So let's get on to linear algebra. My mark is that we're in Chapter 2, Matrices, 2.4 Elementary Matrices, on the top of page 77. It said, you know from section 2.3, last section, that not all square matrices are invertible. And every elementary matrix, however, is invertible. Moreover, the inverse of an elementary matrix is itself an elementary matrix. So this leads to theorem 2.13. If E is an elementary matrix, let me get my pen activated. Okay? If E is an elementary matrix, that implies that E inverse exists, and not only does it exist, but it's also an elementary matrix. Two things. If E is an elementary matrix, okay, one thing they aren't stating, but it's true, it's invertible. Okay, well, they sort of are stating. They're saying E inverse exists. That means E was invertible. But that inverse matrix is also an elementary matrix. Okay? Now, you'll see the reason for this coming up. Here's a statement that's probably going to be useful to you. The inverse of an elementary matrix, E, is the elementary matrix that converts E back to IN, okay, the identity matrix. For instance, the inverses of the three elementary matrices from example 3. Let's go back and do that. The first one, if you've had that, remember that from last time. First elementary matrix we had, I1, was this one, 3 by 3, 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay, that's the elementary matrix E1. Okay, now how we got there, we exchanged row 1 and row 2 from the identity matrix. Okay, so how do we get the E1 inverse? You swap them back again. Okay, and that would be 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay, now that's the same matrix, isn't it? Okay, but let's do our multiply these two together and see what we get. 0, 1, 0, so the first entry is a 1. Second entry, 0, 0, 0, second entry is a 0. Third entry, this is 1, 3, 0, 0, 0. So the top row is 1, 0, 0. Second row, 2, 1, 0, let's see, 2, 1, okay, 0, 0, 0, 0. The 2, 2, 1, 0, 0, 1. And 2, 3, 0, 0, 0, 0. So 0, 1, 0. And then the 3, 1 entry would be 0, 0, 0. This is 0. 3, 2 entry, 0, 0, 0. This is 0. And 3, 3 entry would be 0, 0, 1, 1. So, yep, that's it. Okay? So it was flipping the two rows back again, but remember you do it to the identity matrix, not to the matrix you had. Okay? And sure enough, that is the first one. Now the second elementary matrix we did in the previous problem, example 3. Here was the entry 1, 0, 0, 0, 1, 0, negative 2, 0, 1. That was our E2. Now we got that by negative 2 E1, negative 2 row 1 plus row 3. Okay? Now, what the inverse matrix of that is, this is E2 inverse, is not multiplying by negative 2, but by positive 2. So it would be positive 2 row 1 plus row 3 is the new row 3. So that would be 1, 0, 0, 0, 1, 0, 2, 0, 1. Okay? Now, somehow, pit of the stomach, that doesn't quite feel right. Let's check it and see if when we multiply these together, if we indeed do get the the identity matrix. So 1, 1 entry would be 1, 0, 0. That's a 1. That's right. 1, 2 entry would be a 0, 0, 0. That's right. 1, 3 entry, 0, 0, 0. That's right. 2, 1 entry, 0, 0, 0. That's right. 2, 2 entry, 0, 1, 0. That's right. 2, 3 entry, 0, 0, 0. That's right. Okay. The 3, 1 entry, -2, 0, 2. That adds a 0. 3, 2 entry, 0, 0, 0. That's right. And negative, and the 3, 3 entry, 0, 0, 1. Yeah, that works. Okay. So the inverse matrix of a matrix that you swap 2 rows is just swapping the same 2 rows of the identity matrix. So it's the same thing. The inverse matrix of multiplying, adding a multiple of one row to another row is adding the opposite multiple of that row. In other words, if you multiply by 7, multiply by -7, but do it to the same 2 rows. Okay? So, E3 from before. Now, if you're listening to this, you know I'm able to record again. I'm recording again not because my computer has been fixed and they got it back to me, but I was told it would be ready on Friday. I went by Friday to pick it up. They hadn't been able to even really get started on it well. So what he did, he gave me a loaner computer, which is a Fujitsu like my other one, only it has a smaller screen, and then the portion of the screen I can write on is even smaller. So if it looks like I'm writing really big now, I'm actually writing even smaller, but I'm writing smaller on a smaller screen, but it's a bigger proportion of the screen, so when it records, it's going to seem bigger than what it was before. So I've got to clear this, and then I'll do E3. Now E3 from before, from example 3, was this matrix. 1, 0, 0, 0, 1, 0.
Hey, Doc.
Howdy, how's it going?
All right, I want to check with you. See.
Oh, I thought you brought me lunch.
I can come there and get it too.
No, I'm just kidding. Let me pause this for a moment. Sorry, another instructor came in to let me know something. Okay. So the third elementary matrix we had was this one, which was multiplying the identity matrix, the row 3 by 1/2. Okay? Well, what would you think the inverse of that would be? All right? If you thought, and this was the one that makes the most sense to me, it is multiplying the third row by 2. And that would be 1, 0, 0, 0, 1, 0. Remember, you multiply the identity matrix by that. 0, 0, 2. Let's confirm that again by multiplying these two together. You should get the identity matrix. So the 1, 1 entry would be 1, 0, 0. That's 1. That's good. 0, 0, 0, 0. That's right. 0, 0, 0. That's right. 2, 1 would be 0, 0, 0. That's correct. 2, 2, 0, 1, 0. That's correct. 2, 3, 0, 0, 0. That's correct. 3, 1 entry, 0, 0, 0, 0, 0, 0, and 0, 0. 1/2 times 2 is 1. Yes, that gives you that. We just use matrix multiplication to check those results. So the following theorem states that every invertible matrix can be written as a product of elementary matrices. And here's how that theorem goes. A square matrix A okay, is invertible if and only if. Now this is the symbol I use for if and only if. Another one would be IFF, or you could write it all out. If and only if it can be written as a product of elementary matrices. Okay. Now, when they do the proof, they start with the if and only if. What that means is the left-hand side, the given here, square matrix A, invertible, if it can be written as a product of elementary matrices, that's the if part. But going the other way, if it can be written as a product of elementary matrix, that means it's invertible. So that's what they do, and the theorem there is going to be illustrated by example 4, at least the first part of that theorem. Okay? And so let's do example 4. This is top of page 78. Find a sequence of elementary matrices whose product is the non-singular matrix A. Here's the matrix A. All right. Here's A. -1, -2, 3, 8. Okay. So we want a sequence of elementary matrices that when you multiply them together, you'll get this product. Okay? Now, what we have to do that is, and this is going to be a little on the hairy side because my space is so limited to write, and I've got a lot to write here. Okay, what we have to do is row reduce this matrix, keeping up with what elementary matrices do that row reduction. Okay? And we'll need the inverses of those matrices. Okay? So the first step in row reduction here is multiply the top row by -1. Row 1 by -1. So that would produce this matrix. 1, 2, 3, 8. Okay, the elementary matrix that did that was this one. -1, 0, 0, 1. That's the elementary matrix that did that. I'll call it E1. Okay? Now, at the same time, I'm going to tell you what E1 inverse was. And you might say, why would I do that? You'll see in a minute. Okay? I'll just say it that way. So E1 inverse, remember this is the one you multiply by the reciprocal of it. The reciprocal of that is a -1. So that also is going to be -1, 0, 0, 1. Okay? That's E1 inverse. Next step. This was minus row 1 becomes the new row 1. Okay? Next step is -3 row 1 plus row 2. Okay? So that would be 1, 2, 0, 2. Now the elementary matrix that did that same thing, so this is going to be E2, is going to be 1, 0, negative 3 1. Okay, you do that same operation here, do it to the I matrix, I2, and that's what you get. Now, what's your E2 inverse? Remember what that one was? If you go back to the previous one, that was like E2 before. You just multiply it by the opposite number. Okay? So that'll be plus 3. So that'll be 1, 0, 3, 1. Now, if you have any doubt on any of these, what you have to do is just multiply them together and make sure they're the I matrix. This will be the first one, E1 and E1 inverse will be 1, 0, that's 1, 0, 0, that's 0, 0, 0, that's 0, and 0, 1, that's 1. So that worked. Let's do this one. 1, 0, that's 1, 0, 0, that's 0, minus 3, 3, plus 3, that's 0, and 0, 1. Yeah, that works. Okay. Next step. R2 over 2. So, I'm going to try to get it in over here. I don't know if I can make it or not. That will then be 0. Okay, I'm having trouble. Not only is my screen smaller, but everything's so much closer together, it's hard to get things to that. Okay, R2 divided by 2. Oh, I'm sorry. It's 1, 2, 0, 1. That's the progress of A here as you're doing row reduction on it. Okay, E3 would then be 1, 0, 0, 1 half. And E3 inverse would be 1, 0, 0, 2. All right, check that. 1, 0, that's 1, 0, 0, that's 0, 0, 0, that's 0, and 0, 1. Yep, it works. Okay. It's E3 inverse. I didn't get to label it, but that's what it is. And the last step, the next step, the final one, is row 2, negative 2, negative 2, row 2, plus row 1. Okay? So this becomes, it's not a smiley face, it's an arrow. 1, 0, 0, 1. Okay, the elementary matrix E4 that produces that same result would be 1, negative 2, 0, 1. And its inverse would then be, now remember when we did that, if you recall, this is like the second one we did, you just multiply by the opposite of it. So that would be 1, 2, 0, 1. Okay, check that to make sure. 1 plus 0 is 1. 2 minus 2 is 0. 0, 0, 0, 1. Yeah, that's it. Okay. Now, what we have is remember what to do a step in row reduction is the same thing as multiplying by the equivalent matrix of the elementary matrix that does that same thing. So to get from A to that first step there, it was like multiplying A by E1, but multiplying E1 on the left of A, okay? So to get to the identity matrix, I'm going to write it down here, started with A, multiplied by E1, I wrote it in the wrong place, E sub 1, yeah. Goodness, my stomach is growling so badly, I'm sorry. I hope you can't hear it. E sub 1, then we multiply that product by E sub 2, we multiply that product by E sub 3, multiply that product by E4, always on the left. That gave us the identity matrix. When you did that, you wound up with the identity matrix instead of A. Okay? Now, if you're trying to solve for A, what set of elementary matrices would produce A, then what we do is multiply this by E4 inverse on the left. And what I'm going to do here, I hit the wrong key. Okay. Okay. All right. Here's my I. I'm going to put it way over there. I'm going to multiply this thing by E4 inverse, which would be like multiplying that. If I multiply one side, I have to do the other. Right? But that's just going to be E4 inverse, because multiplying by I doesn't change anything. And then this becomes I, so that goes away. Then I'll multiply by E3 inverse. Okay? If I multiply that side, I have to do this one. Okay? And then these two go away because that becomes the identity matrix. Then I multiply by E2 inverse, and that would be like that. And these go away. And finally multiplied by E1 inverse. Okay, and E1 inverse. And now we're back to A, and this is A as a product of those four elementary matrices, which were the inverses of the elementary matrices that we used to row reduce A to get the identity matrix. We do in opposite order their that product. And then it doesn't matter which one you do first. You could do E1 inverse times E2 inverse, or E1, you could do the E3 inverse times E4 inverse, and just do them any way you want to, and you'll get there. All right. So that leads then All right. So, section 2.3, you learn the process for finding an inverse of a non-singular matrix A. There, use Gauss-Jordan elimination to reduce the augmented matrix AI, and if it reduced it, you came out with I on the left where A had been, then what you had on the right where I had been would be A inverse. So, we'll use the previous theorem, okay? That a square matrix is invertible if and only if it can be written as a product of elementary matrices. So, if that A can be written as a product of elementary matrices, that was your E1 inverse times E2 inverse times E3 inverse times E4 inverse, the one we just did, then excuse me, you can use that to justify this procedure. If I is, start with A, multiply on the left by E1, E2, E3 up to Ek. Then if you multiply both sides of that equation on the right by A inverse, then you get I times A inverse is A inverse. That's Ek times Ek minus 1 times Ek minus 2 dot 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 times E3 times E2 times E1 times I. It seems like it's talking in circles here, and it really feels like it is too. So in other words, a sequence of elementary matrices that reduces A to the identity matrix I also reduces I to A inverse. Applying the corresponding sequence of elementary row operations to the matrices A and I simultaneously, you have, so if you, sorry. Start with a augmented matrix AI. Multiply on the left by E1, E2, E3, and all the way up to Ek. So applying that same sequence to I produces A inverse in. If A is singular, then you can't do either one of them. So the next theorem ties together several important relationships. That last paragraph just seemed to be restating everything that we had just said, so that's all I'm going to do with it, I think, for now. We may come back to it. Okay, let's erase all this, and let's write theorem 215. Equivalent conditions. I think we sort of had this before, but we didn't have as many of them. So what we have here is A being a square matrix n by n. That's what A is. If that's the case, then all the following are equivalent. And here's what they are. First one, if A is invertible. Okay. Now all A n by n matrices are invertible, But if this square matrix is, all invertible matrices have to be square. So it has to be square n by n, but not all n by n matrices. So if this statement is true, that A is invertible, then all these other statements are also true. That AX equal B has a unique solution for every n by 1 column B. Okay. Brr. Now, if that's for any vector B, if that vector B happens to be the zero vector of the right dimension, okay, that's also going to be a vector, then this has only the trivial solution, which is B would be your all zeros, okay? Or your X components would be all zeros. Number 4, A is row equivalent to IN. Okay, now, remember that's how we took our inverses. We do the row equivalent, reduce A with Gaussian elimination, you're going to wind up with IN. Okay, now here's the 5th. This is the one we're adding. I think we had all those before. A can be written as a product for elementary matrices. Okay, so if any one of those 5 are true, all 5 are true. All right. Now that leads to another kind of an issue, kind of a trick. Yes, you call it a trick. With polynomials, one of the key things to do to them, if you can, is to factor them, okay? And then use the pieces to come up with solutions, okay? What about systems of equations? Can we factor those? And what they say here is that the heart of the most efficient and modern algorithms for solving linear systems of AX equal B is the LU factorization, in which the square matrix A, yuck. I almost feel like I'm about to throw up. I hope I don't. Just hit me suddenly. It's the LU factorization in which a square matrix A is expressed as a product. A is equal L times U. Okay? What is that L? What's the U? Where did those letters come from? In this product, the square matrix L, same size as A was, by the way, is called the lower triangular, which means that the entries above the main diagonal are all 0. Square matrix, you have a main diagonal. If it was an identity matrix, that would be your 1s would be on the main diagonal. So any old matrix, if it has a square matrix, the main diagonal are whatever numbers they are. But all the numbers above and to the right of that, every entry is a 0. That's a lower triangular matrix. Whereas an upper triangular matrix, I guess I should write these down. A1100, A21, A220, A31, A32. Oh, goodness gracious. It's an ugly, ugly 3. All right. Goodness gracious. A320. That's a no. A33. Okay. Goodness. My first 2 classes were pretty big classes and no problem, but man, right now with no one else in the room, my hands are freezing. It's hard to hold the pen. And now I'm warming them up. Okay. This is a lower triangular matrix, L, because all the elements, the main diagonal has elements that are non-zero, and everything below it are non-zero, everything above it is 0. Okay? Now, that's a 3 by 3 lower triangular matrix. U, and we'll do another 3 by 3, is an upper triangular matrix. That means A11, A12, A13, 0, A22, A32, 0, 0, A34. Goodness gracious. Okay. The fan on this computer is blowing out warm air. I just want to hold my hands there in that warm air because I'm about to freeze. This is the upper triangular matrix. The main diagonal has entries that are not 0, and the above that are entries that are not 0. Well, not all of them. Some of them could be. But below that, you have to have all zeros. Okay? That's a upper triangular matrix, 3 by 3. So, what is LU factorization? If you have a square matrix, A, n by n, matrix A, if that can be written as a product of a lower triangular matrix L, if A can be written as the product of a lower triangular matrix L, and an upper triangular matrix U, then A equal LU is the LU factorization of A. Okay. Let's look at some examples. difficult. Now, start easy, 2 by 2s. Here is a matrix. 1, 2, 0, 1. Okay? I'm sorry, 1, 0. No. All right. I do not like this kind of problem. All they do is say, voila, here it is. Okay? Why don't they show you how to get it rather than just saying, hey, here it is? That's what they're doing. Let's verify it. Okay? They're saying 1, 0, 1, 1. That's certainly a lower triangular matrix L. Okay? Here's another matrix. 1, 2, 0, negative 2. That's an upper triangular matrix, U, because below the diagonal is 0. The other one above the diagonal is 0, main diagonal. Okay. Okay. Let's verify this. Let's multiply these two together, see if you get A. Okay. 1 plus 0 is 1. Got it. That's the 1 entry. 2 plus 0 is 2. That works. 1 times 1 is 1. That's 2 is 1. That works. And 2 plus 0. Wait, I'm sorry. Yeah, 2 minus 2 is 0. Yeah, that works. That was, they gave it to you and then said, see, it does work. So they're doing the same thing here, not telling you how they got it, but just showing you what it is. Here's A. Now this is a 3 by 3. It's going to be a bit more involved. It's 1, negative 3, 0. 0, 1, 3. And 2, negative 10, 2. Okay, sorry about that. Okay. There's A. That's a negative 10 in the middle of the bottom. All right. They're claiming it's the product of these two. 1, 0, 0, 0, 1, 0, 2, negative 4, 1. Okay. Times, that's certainly a lower triangular matrix L. Here is an upper triangular matrix. One, negative 3, 0. 0, 1, 3. 0, 0, 14. All right, they just came up with those out of the blue, okay? They're saying these, certainly this is lower, certainly this is upper triangular matrix. The question is, do those really multiply to be A? Let's do it to it. 1, 0, 0, 1, that's correct. Negative 3, 0, 0, negative 3, that's correct. 0, negative 9, 0. Wait, I'm just going to do it. Sorry, I got on the wrong one. It's such a little screen. 1, 0, 0 is 1. Negative 3, 0, 0 is negative 3. 0, 0, 0, yeah, 0. Okay, the 2, 1. 0, 0, 0, yep, that's a 0. 2, 2, 0, 1, 0, that's 1. Okay, and the third one is 0, 3, 0, 0, so that's a 3. The fourth, let's see, 3, 1 entry. 1, 0, 0, whoa, 3, 1, 2, 0, 0, that's a 2, negative 6, negative 4 is negative 10, 0, that's a negative 10, and zero, negative 12, and 14 is 2. Yeah, you got it. Yeah, okay. So that surely does work. Now, there's a linear algebra applied that is using what they call computational fluid dynamics, CFD, computer-based analysis of real-life phenomena such as fluid flow, heat transfer, chemical reactions. I'll let you read that. It says aerospace companies such as Boeing and Airbus have an interesting statement here. For instance, the engineers at Boeing use CFD analysis to simulate airflow around the virtual model of the 787 aircraft to help produce a faster and more efficient design than those of the earlier Boeing aircraft. So it really sped things along. All right, I am barely hanging in here. My throat is on its way out. And it's getting harder and harder to talk. And I'm forcing so much volume, not getting it, but trying to force it. And it's really wearing me out, my throat and everything else. So let's see if we can wrap this up. If a square matrix A row reduces to an upper triangular matrix U using only the row operations of adding a multiple of one row to another row below it, then it is relatively easy to find the LU factorization of the matrix A. All you need to do is keep track of the individual row operations as shown in the following examples. Okay? Now, what you'll notice here, example 6, is using the matrix that they used in 5B. That's identically the same matrix. Okay? But we're going to, rather than show there's one, we're going to come up with the LU factorization. So what I'm going to do is erase most of this slide. That was the A part up there. It had nothing to do with the B part. And I don't want this here because I don't want to be guiding myself to the solution. I want to get it independently. Okay, so here is matrix A. All right. Now, remember Gauss elimination? Or wait, I'm sorry. Row reduction. Getting it in row equivalent form, not reduced row equivalent form. That's how you get your upper triangular matrix. Okay? So, you begin by row reducing A to the upper triangular form while keeping track of the elementary matrices used for each row operation. Okay. First thing, we wanted a 1 here, we got it. 0 below it, we got it. So our actual first operation is -2, I say -2 and write -r, -2 row 1 plus row 3. Okay? Now the elementary matrix that does that same thing is 1 0 0 0 0 0 1 0. Okay. That would be -2 0 1. Okay. I'm sorry. I'm doing everything I can to try to hang in. I've got to go get something to drink. My throat is hurting so badly. All right. Sorry about that. It's just getting harder and harder to talk. So, the first step was to do that. I haven't done it to this yet, but let's do it to A. What we just said. That, I'm sorry, it won't be A anymore, but what it becomes. 1 -3 0 0 1 3 and 0 -4 2. All right. Now really, that should be down here. Should be equivalent with that one. All right. Now, we're also going to have the inverses of it. So let me go on and do E1 inverse. Okay. Remember what that was? 1 0 0 0 1 0 and 2 0 1. Okay. Now, all right. Let's review what we wanted. We have a 1 here, both zeros below it. 1 here, we need a 0 below that. So our next step is going to be 4 times row 2 plus row 3. Okay? So I'm going to do this up above. Okay? That's going to be a 1 -3 0 0 1 3 0 0 12 and 2 is 14. Okay? Now, the E2 that did that, doing that same thing, was going to be 1 0 0 0 1 0 0 0 4 1. Okay, and the E2 inverse is going to be 1 0 0 0 1 0 0 minus 4 1. All right. What we have here is now an upper triangular matrix. Okay? And if you flip back one page, you'll see that is indeed the upper triangular matrix that we used, that we showed was the U for this matrix A. 1, negative 3, 0, 0, 1, 3, 0, 0, 14. All right. Now, we kept up with E1 and E2, and at the same time, I wrote down what E1 inverse and E2 inverse. This is so stupid. Okay, sorry, I don't know if you could see that. Windows popped up something and do I want to change colors? I don't know why it did that. So, all right. So here we have our U, review matrix U, upper triangular. Now, if you think about it, what did we do? We started with matrix A, multiplied by E1 to the left, and then E2 to the left, and that's how we came up with U. Right? Now, let's multiply. Now, again, I always forget to do this. Yuck. This thing drives me nuts. Let's move that U over a little bit. Okay. Let's make it U. Okay. If we were to multiply this by E2 inverse, that'd be like multiply this by E2 inverse. These become the identity matrix, and multiply that by E1 inverse, multiply this by E1 inverse. And what do we get? We get the matrix A, which means that E1 inverse times E2 inverse should be L. Well, let's see if they are. Here's E1 inverse times E2 inverse in the right order, in fact. Let's multiply these together and see what they get. 1, 0, 0, that's going to be a 1. 0, 0, 0, that's going to be a 0. 0, 0, 0, that's going to be a 0. So far, so good. Let's multiply the second to 2-1 entry. 0, 0, 0, that's going to be a 0. 2, 2, 0, 1, 0, that's going to be a 1. And 0, 0, 0, that's going to be a 0. Okay? Bottom row will be a 2-1 entry. 2, 0, 0, it's going to be a 2. 0, 0, minus 4. And a 0, 0, 1. Okay? And here we have 1, 0, 0, 0, 1, 0, 2, negative 4, 1. Is that what we had as our L before? 1, 0, 0, 0, 1, 0, 2, negative 4, 1. It sure enough is. Okay? So there we have shown how to come up with these. Not just, hey, behold, here they are, they work, but how you get them. Okay? And just looking back, start with the matrix A. Any square matrix, of course, it's going to have to be invertible for this to work. And just do our normal steps to get that into a row equivalent form. Not reduced row equivalent, just row equivalent. 1 in the upper left, zeros below it. First non-entry in the next row, a 1, 0 below it. If you had more rows, just keep going over like that until you have you've got it in in row echelon form. Okay, diagonals of 1. They don't all have to be 1s, but diagonal entries and zeros below them. Now, as you're doing that, keep up with the elementary row operation, elementary matrices that you use to perform that. And while you're doing that, write the inverses of those. And then notice what you got to get it into that upper triangular matrix. Multiply that by the inverses in reversed order, and that gives you your lower triangular matrix. Okay. So if A reduces to an upper triangular matrix U using only the row operations of adding a multiple of one row to another row below it, then A has the LU factorization. Now notice this one. They kind of cheated a little on us. The first, in that 3 by 3 matrix, the first 2 diagonal entries were 1s, and you didn't have to change either one of them. At the end, you had a 14 down there. That didn't need to be a 1. So in other words, you didn't have to divide or multiply a row by anything, and you didn't have to swap any 2 rows. All you did were adding a multiple of one row to another row to make it into a upper triangular matrix. All right? To do your row equivalent form. Okay. Your L then is a product of inverses of elementary matrix used in that row operation. Once you obtain the LU factorization of a matrix A, you can then solve the system of n-linear equations in invariables. I think we're going to have to stop there. That's the next thing, and I'll go over that before we do example 7. So we'll pick up there at that paragraph near the end down there once you have obtained. Okay? I hope I'll see some people next week. On Thursday. Had nobody here today, which is not good. Hopefully you'll be back on Thursday. All right, I'll end it there.